All right, so our test condition here may seem kind of strange, which is that we have this antenna, very short antenna connected directly to the radio. The antenna is in the house. It's a short antenna, it's just connected directly to the radio. And the purpose is to demonstrate the interference that the power supplies can cause when the antenna is close. And this could be that if you have a sensitive antenna in the attic, so on a certain level, this test isn't realistic. You have an antenna right next to the power supply, but in another way it can be, because one of the things I've noticed is that when the antenna was, 12 feet away from the power supply, it would still be picking this up. So this is just to demonstrate the type of noise that various power supplies produce and what kind of mitigation strategies that we have at our disposal. All right, so just looking at a normal power supply here, DC supply from ASTRON. A lot of people have this power supply. I got it at Ham Radio Depot. Sorry for the lighting condition here, but I'm shooting at night. I purposely only have one light on so that we're contributing the least amount of interference from the light. So let's see, with this linear supply here, what we can see here, I'll turn this radio up. So we'll go back down to around 1.5 megahertz, let's say. And you can hear the interference. And you can kind of see, you really hear it. Kind of see it out here. Persisting here at 2.5 megahertz. Persisting here at 2.8 megahertz. 3.2 megahertz. And maybe it's gone by 4 megahertz, but down here in the AM band, there's I think that this area in here is from kind of the local stuff, the refrigerator, the dimmer switches, that sort of thing. But this is what it sounds like with this normal power supply. It is a linear supply plugged directly into the AC power. Presently, I have the radio connected directly to a battery just to demonstrate what it sounds like and looks like around this frequency range. So what I found is that the linear supply will put some interference in, particularly on the lower end of the range. And so here we go. We're at 3 megahertz now. We'll sweep lower. Down here at 1.9. Down here at 1.4. Starting to hear a little bit of kind of some his 60 hertz stuff going on here. It doesn't prevent us from actually hearing this AM radio station. It's not really, the interference that's there isn't really strong enough to interfere with this radio station. And as we get lower, the noise that is in the air definitely is, becomes pretty serious and debilitating right around 600. Now this is due to the dimmers and that sort of thing. But again, up at around, certainly north of 1.5 megahertz, you don't hear anything or see anything when connected directly to the battery. So now what I've done is I've taken the power cord and wrapped it around this Mix 75 toroid 9 times, which is the most I can fit on this particular toroid. Ferrite toroids, Mix 75, because the interference we're experiencing is at low frequency. I found that in this case, for this supply, wrapping the power cord that goes from the radio, from the power supply to the radio, doesn't affect this particular situation. It is only here. And what we'll do, we'll take a look at this now and see how that has helped. And it's definitely helped. Here we have 2.6 megahertz, 3 megahertz, 3.5 megahertz. Go back down, 1.8, 1.6, 0.4. Let's see, turn it here. And then we get down into this area where, like I say, this noise is just kind of from the household. So this has definitely helped. It's definitely taken a big chunk. It's really improved the situation with this linear supply. And the reason why I'm interested in this is because this is in the low band. I mean, 1.8 megahertz is a legitimate band that we would be wanting to operate in, and so we would want it to be as quiet as possible. So for this linear supply, this is what I found is the mitigation strategy. Next, we're going to be considering this ASTRON supply, which is another one quite common in the ham radio business. And we'll take a look at the interference that this puts out and the mitigation strategies at our disposal. So what we see here is something kind of very interesting and kind of characteristic, it turns out, for switching power supplies and even switching power supplies in household items. And what I mean is this kind of thing that's dancing back and forth and almost looks like it's drawing a squiggly sine wave here. Let's change the span on this so that we could zoom in on that some. Yeah, there we go. And I'll boost this up a little bit here so that we can see that a bit better. So what we see is as we move around here, this kind of thing that draws back and forth, and you can really hear, if you're anywhere near one of these frequencies, you really hear it. It sounds like 60 hertz interference. And this is just everywhere. Let's see. Another one there. No, that's not it. Here's another one here. And we'll go back to our really wide span here just so that we can see this better in terms of where they're located. Anything you see moving back and forth is caused by that supply. Here, 2.82 megahertz, 2.2, 2.4, 2.7, 2.9, 3.1, 3.3, and on up. Let's keep on going and see just exactly how far this stuff exists. It seems like it's getting higher in amplitude as we're going up here. Yeah, it's really very high here at 8 megahertz. Let's see how exactly how far we've got to go up before we get out of this stuff. Still there at 13 megahertz. Turn down this. Okay. You see this just kind of drawing squiggles back and forth and back and forth. It's still there. We're at 17 megahertz. Yeah. So that's the kind of characteristic stuff that we see from switching supplies and especially from this supply. And if I park my cursor on it, you can see, I mean, we got S9 plus, so there's just not going to be any receiving signals when you got this kind of noise being generated by the supply. What I've done is ICOM has really long cables that they give you with the radio. And what I've done is I have wrapped the entire length of the really long cable around this 3-inch toroid. I'm not exactly sure how many turns on this, maybe 20 turns or something like that on this toroid. And it's really helped. What we see is we've gone from an S9 plus to an S4. So it's a lot better. And let's see, this here is 8.5 megahertz. Maybe we go up and see 11 megahertz up here. It's, I think, really improved things. Continue on up here. This is bouncing, maybe actually local interference here. Have to try it with the battery. But let's see, we'll go down here at 6 megahertz. I mean, you can see that that wavering is still there. But at least now other signals are much higher than this, at least in this particular frequency range. We'll continue on down. You might remember that especially at the very low frequencies, it was really prominent. So you can see, we're kind of starting to be down in the AM band here, and you might remember that it was, really noticeable here in the AM, and that's really knocked it down quite a bit. So wrapping a lot of turns of the output of the supply through a common mode choke into the radio has really knocked that down. And this is, for this particular switching supply, that is the mitigation strategy that's available. All right, a bit more experimentation here with this supply here. I found something very interesting. So if we take a look here at around 8 megahertz, what we see signals around S9 in terms of the noise. All right, and that's with the power coming out of the front terminals directly into the radio. So what I decided to try was, what would happen if instead we got the power from the rear terminals? So let's take a look at that. Let's see. So now this is, because this supply has these Anderson power pole in the front, but it's got these alternative ones in the back. And now it's about S6. So it's definitely less coming out of the ones in the back. So I was wondering why, and I'll show you. I've got the cover just loose here. What we got is, you could see that all of the voltage from the supply comes from this, basically the corner of that, and it goes almost directly out the back terminals, but out the front terminals, it has the opportunity to kind of pick up a whole lot more on its way out to the front terminals. So you might remember my big donut here. I was able to get 21 turns on this thing that's 4 inches outside diameter and 3 inches inside diameter. This is from Palomar. 21 turns, but 21 turns consumes almost the entire cable. But nevertheless, this is what it does. So we're able to get the ones from the front terminals down to about an S1. Now that's in the front terminals here. Okay, so now what I've done is I've changed to the rear terminals. So I've got, instead of plugging in here, I'm just coming out of the rear terminals and going into my big donut here with 21 turns. And it's almost completely gone. Not completely, but almost completely. It's really largely gone in this particular configuration. So I wanted to see if there was any way that we can do this without having to consume the entire length of the ICOM power cable. And so I got one of these here from DigiKey. You can see the part number there. This has 17 turns, and this can probably handle the current that we'd be operating under most circumstances. You can tell the wire there just by eye, it's probably number 12 or even number 10 wire wound around this. This is only 17 turns wound around this toroid. And I've got it powered here off the back terminals. So we got the back terminals, we've got this common mode choke, and then we've got going into the radio. Doesn't quite do as good of a job as the big round ring on the back terminals, but it does pretty good. And this is not bad. And for anybody who thinks that this is not really a fair test, that I've got the antenna so close, then we've made a real improvement by using this common mode choke with the back terminals of the power supply on this radio here. I think the approach to use here would be to 3D print a little box with some power pole connectors in which you would put this, and you can just make it so that you would just wire it to the back, to the back panel here, and just put some Anderson power poles on it so that plug your radio into the connection back here, and probably not bother with the front connections. Next we'll move on to this supply, which is also another very common one in the ham radio business, made by Alinco. And when I showed the ham radio output folks my video from the Astron supply, and I said I was looking for something quieter, do you have something quieter? They said, oh yeah, you got this one here. And in case the noise is in your way, you can adjust this noise offset here. And so I was a bit suspicious by that. So kind of like, how about just making a power supply that's very quiet, that you don't need a noise offset? But nevertheless, let's give this thing a look and see how it compares to the other ones. Again, this test is just from the power supply straight into the radio. And this is what we see just here in the low band. You see all kinds of noise spikes going in down here. You might just notice, compare this to the other ones, just all kinds of little stuff in here. And let's see, we'll just keep on going higher and higher and take a look at it. Let's see. Now this hill here was there in all of the tests. And it's just that the kind of the noise floor is just higher, certainly, than it was on the battery. Keep on going higher in frequency. Let's see up here, and got some shortwave radio stations here. 8 megahertz, 9 megahertz, 10 megahertz. So the characteristic is certainly different from what we saw with the other supply. You don't necessarily see these signals kind of dancing back and forth like you do on the other switcher and what I've seen with household switchers. But we'll go down here into the AM band. And what I'm going to do is adjust that control there that they call noise offset while we're watching up here. Try to do that. Let's see if I can move this supply a little bit closer. Make it easier for me to turn that while looking at the radio. So I'm going to turn it clockwise, and you see some of these little things in here just kind of dancing around. Hope you can see that. You see some of the lines here, instead of them being straight, you'll see they're kind of curving left and right. Lots of them here. And this is as I'm adjusting this clockwise and counterclockwise. So probably this control adjusts the switching frequency, and thus you can kind of move things around, but just there sure are a lot of them, you know, and so the prospect of moving it, you know, like maybe helpful, maybe, but then on the other hand, it's sure would be nice if they just weren't there. All right, so here is the same power supply, but this time through the ferrite ring with almost the entire length of ICOM power cable through the ferrite ring. Take a look at this. And let's see, first we'll start here. We're about where we were, 1.5 megahertz or so. And what I'm going to do is I'm going to turn this noise offset while watching this. We'll let this continue all the way straight. You see a little bit of stuff kind of moving around in there, a little bit. But the point I'd make is that just all the stuff is just a whole lot more dark, meaning we just don't have as much of this noise, that the noise floor just isn't as high with all of those turns wrapped through there. Let's continue on up the frequency. Let's see if it remains dark. And again, this hill is just there. It's just kind of a part of the environment here. Keep on going up. Got our shortwave radio stations. Shortwave radio station down in here. But the fact that all this stuff is just so much darker now, it just shows that we've really, for one thing, that power supply is really making a lot of noise, and that common mode choke has really helped to attenuate that noise in there. So here we're 7.3 megahertz, continuing on up 8.2, 10 megahertz. In a second, I'll go back to the battery and we'll see this. Probably up in here is in the environment. Yeah, I'm pretty sure all that's in the environment. But nevertheless, down here, 7.8 megahertz. You could look at the video before I put this common mode choke on. It's a whole lot different. It's a whole lot more dark now than it was without the common mode choke. All right, I'm in a different location here, so the environment's a little bit different, but we have this Alinco supply connected directly to the 7610 through the normal ICOM cable. We'll just take a look at the interference that we're experiencing here. Take a look here in what I call the AM band. This is what it looks like. Just kind of take a look at this here. Starting to get into some, this particular house is really noisy. We got a lot of RFI sources in this house. But nevertheless, we'll just kind of scan around the bands here, see what it looks like. And you see we get into these areas where it's just completely yellow, signal level S9 interference. And this is a combination of this household noise plus the noise that this Alinco supply is putting in. I'll go up to around 10 megahertz. Just so you can kind of get a feel for what it looks like. All right, and then we'll put the supply through this filter I made, and this consists of those two common mode chokes. And I made this 3D printed box and put this, put these Anderson power poles on it. Let's see if I could do this with one hand. It's like that movie that said, filmed with iPhone. Let's see. Yeah, not gonna, maybe, sort of. Let's see. All right. All right, so and what you see is we still have this household noise, this kind of rolling thing, but we were deep into yellow here and we're not there. We were at S9 before and we're way lower now. And we still have the rolling, but we're not deep into the yellow like we were before. And like I say, this is just, we've got so many RFI sources in this house. And then down here into the AM band, let's see. We were around there. And so you can compare how dark blue this is to what it looked like before we put the filter on. And I think that this filter is the most effective thing that I've made. It seems more effective than the donut rings that I had. Then wrapping all of this cable, I think it's about 12 feet of cable around a single ferrite ring. This filter is the most effective thing that I've been able to make.